Hi kids. Today we are going to be talking about three-dimensional vectors instead of two-dimensional vectors. Three-dimensional vectors work very similar as two-dimensional vectors, except for now we will have a three-dimensional space, x, y, and z, instead of just our xy plane. So when we are doing the actual computations, works very similar. Our unit vectors I and j still exist, but now they have a third component, and we have a third unit vector k, which has a horizontal and vertical component of 0, but now that third vector or component, the z component, is 1. So we can use our three standard unit vectors to write a vector as a linear combination, or we can write it in component form the exact same way we did, where we do terminal point minus initial point. You can kind of see how the three-dimensional plane works. It's like we took our normal xy plane and then added in the z plane, but we rotate our xy plane so that it's flat, and then our z plane goes up and down, where positives would be up, negatives down, positive y is to the right, negative y is to the left, positive x is to the left, and negative x is to the right. So let's do some computations. Go ahead, take a second, write this down. Example 1, find the component form of a vector v with the initial point 2, 4, 1 and terminal point 3, 5, 2. And then we're going to find a unit vector in the direction of v. So I'll give you a second. You might want to pause this to finish writing the problem down. All right, so in order to find our vector, we do it the exact same way. If we're going to take our terminal point, 3, 5, 2, and we're going to subtract our initial point from that. So 3 minus 2, 5 minus 4, and 2 minus 1. So our vector v is 1, 1, 1. To find the unit vector, we're going to divide by our magnitude, just like we did with two-dimensional vectors. So our magnitude is going to be the square root of 1 squared plus 1 squared, now plus 1 squared. So the exact same thing as before, but now it's 3 elements being squared. So that gives me the square root of 3. So my unit vector is going to be my vector 1, 1, 1 divided by the square root of 3. Which, when we simplify, gives us square root of 3 over 3. Square root of 3 over 3, and square root of 3 over 3. So there's our unit vector in the direction of v. All right, example 2. Find negative 135.04, negative 2. So the dot product works exactly the same in three-dimensional plane as it does in two-dimensional. We're going to take our first component times our first component plus second component times our second component plus third component times our third component. And again, if you need to pause for a second to write the problem down, please do. So negative 1 times 0 is 0, plus 3 times 4 is 12, plus 5 times negative 2 is negative 10, so we end up getting 2. All right, example 3, find the angle between U, which is 4, -1, 3, and V, which is 0, 1, 5, and approximate to the nearest tenths. So in two-dimensional, we have cosine theta equals U dot V over magnitude of U times the magnitude of V. It's going to be the exact same thing. Now that we know how to find the dot product of two vectors and the magnitude of two vectors, it's the exact same thing. So we're going to take the dot product of U dot V over the magnitude of U so we get 0 plus -1 plus 15 all over the square root of 26 and the square root of 26. So that's 14 over 26. So when we do inverse cosine of 14 over 26, we get theta equal to 57.4. degrees. All right, next example, the initial point of the vector v is p 0, 3, -3, or sorry, 0, 2, -3. What's the terminal point of q of this vector? So I know that I get my vector v by taking the terminal point minus the initial. So what we're going to do is we're going to set each component equal to each other. So 6 is equal to x1 minus 0. -1 is equal to x2 minus 2. And 4 is equal to x3 plus 3, and then we solve. So we get x1 is 6, x2 is 1, and x3 is 1. So my vector q is 6, 1, 1. And I misspoke. This is not a vector. This is a point. Point q is 6, 1, 1. All right, and our last question, determine whether the points P, Q, and R are collinear. So we're going to determine if the vectors PQ, QR, and PR are parallel. It's essentially what this is asking us to do. So you do not need to plot these points, but I want to show you how to plot a point in the three-dimensional space. So we have x, y, z. So the point 1, -1, 3 is 1, -1, and then 3. So what you do is you make like a rectangle with your x and your y coordinate, and then you go up 3. So that's where that point would be about, where we went 1 on the positive x-axis, 1 on the negative y-axis, and then up 3 for the z-axis. So that's where our point P would be. Our point Q is 0, 4, -2, so none on 0, but we go right 4, and then down 2, so there-ish, and then 6, 13, -5, same idea, 6, 13, and then -5 would be down, so it'd be somewhere down over here. It's really hard to see three-dimensional points and to graph three-dimensional points, which is why we typically don't do them without the use of technology. All right, so what we're doing is we want to determine if the points P, Q, and R are collinear. So P, Q, and R. So what we're going to do is we're going to find vector PQ, find vector QR, and find vector PR, and determine if they're all linear combinations of each other, if they're parallel. So for vector PQ, we're starting at and heading in the direction of Q, so P's our initial, Q's our terminal. So 0, -1, 4 + 1, -2 - 3, which is -1, 5, -5. Vector QR starts at Q and heads in the direction of R, so Q is our initial, R is our terminal. So we'll have 6 - 0, 13, -4, and -5 + 2. So that gives us 6, 9, -3. And then our third vector, PR, it has an initial P, terminal R, so 6 - 1, 13 + 1, and -5 - 3. So that gives us 5, 14, -8. So none of these are linear combinations of each other. You can tell just by looking. So they're not collinear. All right, so as you've seen, that working with three-dimensional vectors is very similar to working with two-dimensional vectors. We just have a third component. So at this time, you can show the substitute you filled in your notes if you'd like, but homework is in in your textbook. So if you go pull up our Google Drive, we're in chapter 11 now, so that's not in the normal book that we're typically in. It's a separate PDF document that says chapter 11, so make sure that you're using that instead of the whole entire online textbook, okay? I also have an updated version of our calendar on our Google Classroom if you would like to look at that, or I'm sorry, our Google Drive if you'd like to look at that to kind of see how the snow day affected, when quizzes and tests are, etc. All right, I'll hopefully be back tomorrow. So I will see you all tomorrow.